Okay, greetings, welcome to week 12, and today we will be quickly going through suspension as a module. So, the suspension module in this particular course is more of an informative module, and we do not have much of numerical content on it because that is typically covered in our vehicle dynamics course under the title of vertical dynamics, where we talk about various aspects. So, what are functions of a suspension system? It should provide a uh, good ride quality comfort by minimizing the effects of road disturbances. So, it should isolate road. Second, it should hold the road. By that, what we mean is we want to minimize the variation in normal forces acting on each wheel, so that vehicle stays put on the road. And also, it should ensure that the roll and pitch motions of the vehicle during cornering and combined cornering with accelerating or combined cornering and braking scenarios, the vehicle is uh, still stable and controllable to the driver. So, what are the challenges in suspension? Challenges include uh, conflicting requirements. There is a large variation in loading conditions. For example, uh, if we were to consider trucks, for example, say, then an unloaded truck will be like 5,000 kilograms and a fully loaded truck will be 15,000 kilograms. So there is large variation in uh, operating mass or loading condition of the vehicle. Right, that is one portion of it. Second requirement is level versus uneven road. So how it should behave on a flat road surface versus how it should behave on a uneven road. So those are also conflicting operating scenarios. Then there is straight line motion and cornering. So some attributes of suspension will help us in straight line motion, but it may deteriorate the cornering capabilities, whereas some aspects will help us in cornering, but may lead to subpar performance during straight line motion. And same thing can be said about acceleration and braking. So the choice of suspension also is influenced by drive and steering requirement. For example, if like it will be different the way you choose the drives. Like if you take older SUVs, they used to have leaf springs, and now we'll have something else. So that is if you are working with a front drive car which has engine in the front, the space might be lower. So we'll have to tweak some suspension design. So availability of space also matters there, right? And of course, like the space and cost constraints. So there are three types of suspensions which we will be discussing. First is a rigid axle, second is independent, and third would be semi-rigid axle. So what constitutes a suspension? It has an energy storing elastic element. Second is that it has a dissipating element, and it has a set of mechanical elements like linkages, which connect the sprung mass, which is the vehicle body, to the unsprung mass, like whatever is below the suspension. Right. So the idea to have spring or an elastic element is to provide a restoring force proportional to deformation of suspension in opposite direction, right? If we were to load a spring, it gets loaded in, say, x direction, so it will exert a force in negative x direction. The reason why we have energy dissipating element is because the energy imparted to the vehicle by the road as the vehicle is moving on the road has to be dissipated so that it does not reach to the driver, right? So it this provides a dissipative proportional force to the suspension deformation rate, right? So the spring is essentially, the spring force would be k into x, and this will be, say, c into x dot, right? The damping force would be c into x dot. So the spring and damper are important things for the suspension's uh, dynamic response, and its kinematics is governed predominantly by the linkages we have. So let's take a look at components of a suspension. There are springs like leaf spring, torsion bar, coil spring, and pneumatic spring. Each one of them will have some advantages and disadvantages, which we'll be looking into it as we move forward. Then there are dampers or shock absorbers. It can be monotube or a twin tube design. So let's take a look at leaf spring. So this is just a a strip of metal with with a curved shape, so that if there is some motion at the axle tube as pointed here, and we are constrained at the hanger or at the shackle, this is going to move up, and as it moves up, there is some deformation in the spring. Since one single unit is not sufficient, we add a few of them. So, and this is also very easy to construct, right? So it is commonly found on light trucks, SUVs, vans, and some passenger vehicles, but it's predominantly found on commercial vehicles because it's certainly cheaper to work with, right? As cost is a critical component in commercial vehicles. So all the leaf springs are fastened through a center bolt, and they are also held together by some clips. Right? It is very simple in design, and you just need to add little more. You may add one more of strip to change the stiffness. Also, there is friction between these leaves. Essentially, this friction provides some level of damping. Additional dampers can be added to this so as to uh, improve the damping characteristics of overall suspension. Uh, what are the drawbacks of this design? They are heavy, they get weaker with time, and they are susceptible to sag. So as this ages, it is going to sag. Then second thing is a torsion bar. Here, yeah. So second thing is a torsion bar. It consists of a steel rod where one end is connected to the suspension arm of the wheel, and second end is connected to the chassis, which is a fixed end. Okay, so the vertical motion of suspension arm results in twisting of this torsion bar. It is also used in trucks and SUVs. It is durable, it takes lower space, that is an advantage of this kind of design. But the effective spring constant is difficult to adjust in this kind of a system. It will depend on the stiffness of the bar chosen. Now, coming to the most common type, the coil spring. It is essentially a steel bar or rod which is wrapped as a coil. It is very compact, but they require control arms to limit their longitudinal and lateral motion. So the function with the control arms is that the spring do not get buckled. So the shape of the spring essentially should be retained, and it should only take axial loads irrespective of the motion. So they need additional support in that sense. Then one more thing is pneumatic spring. It is essentially a, a thick bag of rubber in which air can be filled. So it is used in buses and trucks, like some of the premium buses you see even advertise air suspension. Right, it is normally a two-ply rubber cylinder filled with compressed air. So of course there is additional requirement of an air compressor and reservoir to store air and a control system. Uh, and a gas spring for this kind of a system, where the stiffness can be adjusted by changing the air pressure, right? The control system can modulate the air pressure to modulate the deflection. So it can be it will be of an active type suspension, where this kind of mechanism allows us to dynamically adjust for that if need be. So uh, this kind of suspension also prevents sagging, sways and bottoming out, resulting in a smoother ride. So for example, if loading condition goes higher, we can increase the pressure or decrease the pressure, so it provides some additional support, sorry, adaptability to the vehicle's operating condition. So let's quickly go through some terminologies. First is sprung mass. Sprung mass is something, a mass which is supported on the suspension, right? It is the vehicle body. Unsprung mass is between the suspension and the road. So if right, this will include your wheels and axles. So you can divide it. The suspension essentially separates or instead of separates, connects the sprung mass to the unsprung mass. So if we call something as a loosely sprung vehicle, they have a softer spring and can provide smooth ride, but they compromise on road holding and cornering characteristics. On the other hand, there are tightly sprung vehicles which have better road hand holding and cornering characteristics, but they result in a rougher ride. So a designer has to somewhere strike a balance between uh, these aspects, the comfort of the driver and how it reacts. Now coming to the shock absorbers, these are oil filled telescoping types. They are commonly used. There are twin tubes and monotubes. So let's look at a twin tube shock absorber. So there is an upper mount which is connected to the vehicle body and a lower mount which is connected to the uh, unsprung mass. There is a piston rod which moves uh, in a pressure tube which is filled with oil. So what we have here are some discs with holes in it. Okay, so what actually happens in such kind of thing is, when there is displacement of the piston rod because of the uh, vehicle's vertical motion, the oil has to pass through these holes in the disc. Okay, so this passing of oil through those holes essentially creates the resistance or resistive force. Of course, if the velocity of motion of the piston rod increases, this force will be higher, and if it is low, it can easily move through the oil. Uh, and that is why we get the force equation for a damper as F equals to C into X dot. Okay. Then there is a monoshock uh, absorber. So here uh, there is an inner tube and an outer tube. So the inner tube essentially uh, is the pressure tube, and the outer tube is the reservoir where excess oil can be stored. In this kind of a design, there is oil and there is pressurized nitrogen gas, right? So this does not have a separate reservoir tube. The fluid flows between the two chambers via the main piston orifices, and a floating piston is supported on compressible gas. So typically nitrogen is used. So since this is a floating piston, there is some possibility of vertical motion of this piston, right? Of this, what can I? Yeah, of this floating piston as well as this, right? Then there are control arms. Why are they necessary? A control arm is needed to hold or complement uh, the springs. So a control arm holds up the steering knuckle, bearing, support, or axle housing. The control arm is connected to the steering knuckle by a ball joint as shown here, right? So the steering knuckle is something onto which the wheel is mounted along with the brakes, and it can rotate. Okay. The control arm is free to move up and down with the suspension. So let's take a look at passive suspensions and then we'll move to active suspensions. Typical suspension systems are passive systems in a sense that they use only a spring and a damper with constant spring constant and a constant damping coefficient. These kind of systems represent a compromise between various functions of a suspension system and is usually a trade-off between ride quality or road holding. Then there are semi-active suspensions and active suspensions. A semi-active suspension system uses a variable damping element such as a twin tube viscous damper in which damping coefficient can be changed by varying diameter of the orifice. And then there are active suspensions which uses an electronically controlled actuator that is placed along with the spring and the damper to provide improved performance. Right, this is where the pneumatic spring or air suspension can be utilized. Then there are other magnetic types as well, where by providing current or generating magnetic field around the damper, its damping characteristics can be changed. So let's take a look at this in a dynamic system perspective. There is the input is rough or irregular road profile. The output is sprung mass acceleration and tire deflection. The sprung mass acceleration corresponds to the ride comfort and the tire deflection is corresponding to road holding. So this is essentially two conflicting requirements. So the suspension behaves like a low pass filter to attenuate the impact of road disturbances while maintaining a trade-off between the above two requirements, right? So essentially, when we are sitting inside the vehicle, we will not feel the minor bumps which are because of smaller gravel or something, but larger variations like speed bumps will pass through. So smaller sized gravels are there are a lot of them, and they produce a signal which can be thought of as low amplitude and high frequency, whereas something like a speed bump will be a low frequency because it's larger in size, uh, and it is low frequency because it's larger in size and it comes less often. So something like a speed bump is what we can feel, like allowing the low frequency signal to pass, but something like a gravel we may not because it is a high frequency signal. So essentially the suspension behaves like a low pass filter. The classical passive suspension design problem is that to choose the suspension stiffness and damping to provide a good trade-off between ride comfort and road holding subject to bounds on suspension deformation or travel. So you would have seen like two coil springs in some bikes in suspension, and if you consider taking a look at a truck, you will see that some leaf springs are not making contact with some leaves. So essentially what we are doing there is having a primary spring and a secondary spring. So if the suspension travel becomes too much, the secondary spring comes into action and suppresses the it suppresses the it increases the stiffness, thereby uh, reducing further potential for travel. And in so a classical suspension design problem, again coming back, is to provide a good trade-off between ride quality and comfort, and an electronic suspension are designed to provide an optimum trade-off. right? Where depending upon operating condition, one may prioritize better road holding or better ride comfort, and the and the suspension components like the spring stiffness in case of uh, pneumatic suspension can be tuned or can be modified to provide what is defined as optimal. The electronically controlled suspension uh, has an energy input. In case of active suspension, energy is added to the suspension, and in semi-active suspension, its response is electronically modified with no significant addition of energy. Right. Now looking at the bandwidth of the control element or the actuator, this characterizes the corresponding response of a closed loop suspension system. So here we are considering that it is an active system. So let us quickly go through categories of active suspensions. First is a road leveling suspension that has an actuation bandwidth of 0.1 to 1 Hz, which is well below of the primary suspension dynamics. It responds to static load variations to maintain ride height and attitude. So the power consumption in such a case ranges in uh, hundreds of watts. Second is slow active suspension, which has bandwidth of 1 to 5 Hz in between the body and wheel dynamics. The control input is the suspension force through an actuator with mid-level power consumption, and a fully active suspension which has higher bandwidth even up to 30 Hz. So here the actuator is working significantly to attenuate uh, the road forces generated up to 30 Hz, and here the power consumption will be significantly higher. Now looking at the bandwidth of semi-active suspension, here an adaptive suspension has a slowly modifying damping arrangement that is an open loop architecture, right? Open loop architecture in the sense that there is no feedback into the system, uh, okay, with a bandwidth of 1 to 5 watts and power consumption is a few watt. Semi-active suspension, here the damping can be varied using a closed loop control system with a larger bandwidth of 30 to 40 hertz, and power consumption will be in tens of watts. So let's not get into historical developments. Let us see where semi-active suspensions can be applied. So first is the classical case where suspension is used from wheels to chassis placement. Then there is chassis to cabin placement. It can be used in large vehicles where the driver cabin is mounted separately onto the main chassis. Right. And then there is cabin to seat placement. This is used in large off-road vehicles to provide better ride comfort to the drivers. In fact, cabin and seat placement has become this area has good potential to come into passenger vehicle market uh, from recent observations. So then semi-active suspension technologies, how are these things working? So first is electrohydraulic, which is based on solenoid valves that can change the damping by varying the size of orifice. Second is magnetorheological or MR dampers. Here the viscosity of damping fluid is varied by changing a magnetic field. So first one affects the orifice, second one affects the fluid, and then third is electrorheological, where the which also affects the fluid, where its viscosity is modified by changing the electric field. Yeah. Now coming to classification of suspensions. First is a dependent type. A dependent type suspension means the two wheels are connected. So if one wheel is going up, the right, it will cause, for example, here this is a rigid axle suspension where one single rigid axle connects both the wheels, and it is over it the vehicle, the sprung mass rests. So here, if one spring is getting compressed, the other spring is also getting extended, right? Whereas in independent suspension, we see that one wheel's motion does not affect the other wheel. Here, by use of mechanisms, we prevent, right, we can have independent motion for each wheel. So, a common one used is a McPherson strut suspension. It is a type of independent suspension. It has one control arm and a strut assembly. So, the strut contains both the coil spring as well as the shock absorber. So, it's compact in that sense. And the top of it is connected to the vehicle body, and lower one is connected to the steering linkage. The second one is called double wishbone or A-arm suspension. This one has an upper arm as well as a lower arm. This is susceptible to side motion called scrubbing. So yeah, and so there is a question: a shorter upper arm, does it introduce positive or negative camber? So if the upper arm is shorter, that means uh, it will introduce negative camber, right? Then second type is trailing arm suspension. This is another type of independent suspension. Here there is a trailing arm which is attached to the chassis, which so the vertical motion of the vehicle would lead to rotating motion of the trailing arm about this axis, which will end up compressing the spring as well as the damper, right? So this would not have side to side scrubbing, but it will take up more space. This kind of things can be found on sometimes on rear wheels of the cars, especially of those which are front wheel driven. So next option is solid axle leaf spring suspension. It is a dependent type of suspension, and the leaf spring is usually clamped to the axle, and the shock absorber is bolted to the axle, right? So you can see the spring here and a shock absorber. Yes, so this spring, which is not connected here, which is not touching these springs, is a secondary spring. So when the deformation of these leaves goes too high, this additional spring or set of springs will come in play to provide to significantly increase the stiffness. And these are simple and cheap, but does not provide great ride quality, and it has significant sideway movement. Next is solid axle but coil spring type of suspension. Here, the coil springs are connected to the axle and to the vehicle body. This is also a dependent type of suspension, and a pair of control arms provide the lateral support to the axle. So, this is another type. Then comes the beam axle suspension. Okay, here the this is a dependent suspension used commonly in front wheel driven cars. The rear wheels are attached to the end of the beam. The vehicle is connected to the beam through springs and shock absorbers, and two trailing arms connect the beam of the vehicle. And for extra stiffness, there is some panhard rod. Now, what are anti-roller stabilizer or sway bar? right? So this minimizes the roll motion of the vehicle, and it is connected to the bottom end of the suspension component from both the sides. So if this is the anti-roll bar, this motion causes twisting in this, which results in some holding force on this side. Yeah. Second is a panhard rod prevents side to side rear axle moment when cornering. Okay, one end of it is fastened to the axle and other is fastened on the opposite side to the vehicle. Now there is a quarter car model which is shown here. It is 2 degrees of freedom, right? Where ZR is the input, ZU is the vertical motion of the unsprung mass, and ZS is the vertical displacement of the sprung mass. Okay. So the governing equations can be formed by drawing the free body diagram and balancing the forces here, right? So there are Kt, which is the stiffness of the tire, Ks, which is the stiffness of the spring in the suspension, Bs is the damping coefficient of the damper, and Fa denotes an active force which is applied by an actuator, right? If we were to consider a active suspension. So this is how we can write the governing equations for sprung mass as well as unsprung mass by drawing the free body diagram, and these can be written into a state space form where state variables are chosen like this. Okay, Zs minus Zu, that is one variable, Zs dot, Zu and minus Zr and Zu dot. So they are the suspension deflection, sprung mass velocity, tire deflection, and unsprung mass velocity respectively. So the governing equation can be written in this form where there are two inputs. First is Fa, which is the active suspension's input, and Zr dot, which is the input coming from the road, right? So input coming from the road as well as what we are giving to the actuator is going to impact how my states will evolve. That is how X dot would evolve. Okay, where A and B and I matrices are given here. Okay, so to obtain an equation for a passive system, we just have to substitute Fa equals to 0, and we can write this as uh, so we can get its natural frequencies. Okay, when the tire stiffness is much higher than the suspension stiffness, right, we can write the two frequencies as Ks by Ms and Kt by Mu. So the tire stiffness and the mass of the unsprung mass, and the suspension stiffness and the sprung mass, right? So these two frequencies correspond to the sprung mass mode and the unsprung mass mode respectively. So various transfer functions can be defined where we take different attributes. So here L denotes Laplace transform. So if you were to write an expression for Zs double dot and take its Laplace transform and take its ratio to the Laplace transform of Zr double dot, where now the input here is the road and output we are considering is sprung mass acceleration. So it's called acceleration transfer function. The smoother the outcome of this transfer function is, the better ride comfort we are going to get. Second is called rattle space transfer function, which corresponds to the deflection of the suspension. Here the input is again the road, and output is the difference between travel of sprung mass and unsprung mass. And finally, the tire deflection transfer function, which corresponds to road holding. Here we are interested in how much the input of road is impacting the deflection of the tire. Right, the deflection of the tire is given by Zu minus Zr. So if we take Laplace of it and take its ratio to Laplace of Zr dot, we are going to get the tire deflection transfer function. So these three transfer functions are going to give are going to behave in a different way for a given input. So the idea is to minimize all three in such a way that it fulfills the objective. Okay, so in some optimal sense, or to modify those. Uh, so for example, we had Fa, which is the active force. So we can modify that Fa in order to obtain better characteristics in each one of these depending upon the operating condition. Okay, so these terms may be important in terms of the exam. So first term is bump, or compression or jounce. It's an upward displacement of the wheel relative to vehicle body. Second is rebound, extension or droop, right, which is downward displacement of the wheel relative to the vehicle body. So bump is something when you go over a speed breaker, and rebound is something which happens when you go over a pothole. Then there is heave, which is vertical upward motion of the vehicle body without roll. There is influence of camber, steering angle, spring and damping forces, tire vertical forces, uh, and hence the forces of at the tire road interface. So all these things would impact how the forces at tire road interface will be perceived by the steering system. Sorry, by the suspension system. So the standard ISO 2631 part 1 defines these things. So the frequency of 0.5 hertz to 80 hertz corresponds to health and comfort. Okay, zero point 0.1 to zero point 0.5 hertz may result in motion sickness, and what we are interested in is vibration dose value, uh, which is computed this way, right? Integral of AWT power 4 dt and power 1, so fourth root of this, where AW is the weighted acceleration considering time duration t. This is how we can calculate that. Then there is something called crest factor, which is modulus of the ratio of maximum instantaneous peak value of AW to its RMS value. Okay, so if the crest factor is up to 9, this alone should suffice. So there are various methods for characterizing or capturing how much of vibration does get transmitted. Okay, so this will characterize the ride comfort. Okay, then let's take a look at vehicle vibrations. There are excitation sources like road roughness, and there are onboard sources like tire and wheel assembly, drive line and engine. Uh, okay, so We have ride, which is commonly used in context of tactile and visual vibrations, typically up to 25 hertz. Then anything which we can hear is getting characterized as noise, typically above 25 hertz. In terms of dynamic system perspective, the excitation source results in a vehicle vibration response which determines passengers' perception to ride. So if we were to not hear too much of noise, and if we are not listening to too much of noise and cannot see it, that means we would categorize that as a good the perception will be in a good category. So what is road roughness? It is random deviations in the road profile that includes potholes as well. It is characterized by a broadband random signal, which is represented by PSD or power spectral density functions. Right. If you were to take or capture a road profile uh, over a range of like for a stretch of road, and then apply Fourier transform to it, right, it would result in a plot of amplitude versus frequency, which is the power spectral density plot. So the spatial frequency is expressed as a wave number with unit called cycles per meter. It is inverse of wavelength, and multiplying the wave number by vehicle speed converts the spatial frequency to temporal frequency. Uh, right. So how do we perceive the profile of the road also depends on what speed we are going. So by multiplying the wave number by vehicle speed, we can convert the spatial frequency to temporal frequency. Okay, so typically the power spectral density of road elevation decreases in amplitude with increase in wave number. Uh, a more meaningful measure for this kind for vibration is acceleration, and hence uh, that is used in ride evaluations. So we have some process given here. Next is impact of vehicle speed. So at a given temporal frequency, the amplitude of road profile acceleration input increases as square root of wheel speed. Okay, so if we consider the road elevation as z is the amplitude, w is the wave number, and x is the longitudinal road displacement, then we get uh, the road elevation as uh, zr equals z into sine 2 pi omega x. Replacing x with v into t, where v is the vehicle speed and t is time, we get this expression, and if we differentiate it twice, we get the acceleration, right, the vertical acceleration imparted by the road. So as you can see, its frequency depends on the vehicle speed, and its amplitude is proportional to square of vehicle speed. Other points to look for is that front and rear wheel road profile input. uh, so this would excite a bounce and pitch motion. For example, if front wheel goes onto a road bump, then the rear would follow the same. This would result in excitation of a pitching motion. Similarly, left and right road profile inputs would excite a roll motion. So essentially, for a given roll resonance frequency, which is property of the suspension and the vehicle, lower speeds would result in comparable road and vertical inputs. This would result in vibration composed of roll and bounce motions. Second point is tire wheel assembly. It consists of the tire, wheel, hub, and brakes. So this is part of the unsprung mass. So if there is some kind of non-uniformity in this assembly, it is going to act as one source of vibration. Okay, there are three major non-uniformities. First is mass imbalance, dimensional variation, and stiffness variation. Right, force variation, which essentially excites the ride. There are variation in the vertical direction, longitudinal direction, and lateral directions. And there are moment variations also because of contribution from the steering system. This may be variation in overturning moment or aligning moment and rolling resistance moment, which comes from the tire. So the mass imbalance occurs when there is non-uniform mass distribution about the axis of the wheel rotation. Okay, so if there is about the axis, there is static imbalance, which produces a force which produce radial and longitudinal excitations. So this kind of imbalance is something which these imbalances can be taken care of during wheel balancing. Right. Second is dynamic imbalance. It causes a rotating torque on the wheel, resulting in variation in overturning moment and aligning torque at the wheel rotation frequency. This is important on steered wheels since this excitation may produce steering vibrations. Okay. Second is dimensional and stiffness variation. So uh, it's called radial runout. So during manufacturing of the tire, it will not be a perfect circle. There will be some tolerances, some uncertainties in the process, resulting in non-uniform tire. So these non-uniformities may result in excitation of forces at the axle with wheel rotation. So then these radial forces, as you can see, they repeat in pattern when you are rotating the right. This is a spatial pattern and it gets repeated in time as you rotate the wheel. So this is measured at a fixed radius when the wheel rotates. The force is characterized by the amplitude of the corresponding harmonics, which are related. First harmonic is related to radial eccentricity, second one is related to ovality, and third one corresponds and higher order harmonics. The higher order harmonics corresponds to the effect coming from tire construction processes. Third source is the powertrain, right? As the engine rotates, right? As the uh, engine is into as the engine is operational, it results in some vibrations. That is also something which affects the suspension dynamics. So that is all we have on suspension. And do you have any question? Hello. Okay. So thank you for joining. Then good luck for the NPTEL exams if you are studying for it. Yeah.
So, numerical question we want to solve solution.
Uh, I think the last session I have to upload. See,
Um,
the numerical solution problems in this are, what do I say? Not much. We have only gone through derivation in the classroom. The details of suspension dynamics are by and large taught in our vehicle dynamics course.
yes.
So this is kind of a this course has been somewhat like that, where majority of it is a theory portion and uh, only few of them are numerical. So
Okay, sir.
right, I think for all the portions where we could do numerical, I have done that.
Numerical question on efficiency. We want to some. If you have
Efficiency of
engine efficiency of engine or powertrain, sir. Yeah.
uh, so see that all those things require me also to prepare. You can revisit the sessions where we have done. So what I can rather recommend you doing is take a piece of right, take one or two A4 sheets and write down all the formulas related to these things, right? Say for example, how do you calculate engine efficiency? How do you calculate transmission various attributes? If you can write it down in one or two sheets of paper, that is something which will serve as a good summary to revise, and it will keep things concise for your preparation for the exam. So
Okay.
okay, that's what I can recommend at this point of time.
Okay, sir.
Yeah,
Thank you, sir.
thank you. So are there any further questions?
Sir, just I want to say that I really enjoy attending this course, especially the videos and the way
Mm-hmm.
the thing has been presented over there. Actually, most of the time it may happens that I go get bored after a certain period of time watching the videos.
Mm-hmm.
But here, I just keep on watching. Like it becomes a habit to watch the video
Oh.
since last 10 days. Like we used to watch the some videos or web series on ott, but this time it's like a addiction to watch the this lectures daily. So it's really interesting, and the way the thing has been presented is really very simple and interesting. Thank you, sir.
Yes, so I'll be happy to pass on your feedback to Professor Shankara. I think he has done a phenomenal job in teaching all of us these both of those courses. And if you have not done our course on control systems, I recommend you to go and check it out. It is presented in a very simple way, which gives you gist of it, and it is slightly heavier mathematically than this course, but it is good one.
Pardon,
Uh,
sir, which course you say?
we have a control systems course,
Control system. Okay,
yeah,
control
yeah,
system.
by
Okay,
Professor Shankar Rao, and that's
okay,
also a equally good course presented in similar way.
okay. It's in I think in the next sem.
Yeah,
It's
it
in
will be in
even.
the next semester.
Okay, it's in the next sem. I will surely like to go for that, sir.
Yeah, uh, I'm
Okay,
glad
okay.
you liked our course.
Thank you, sir. Thank you.
Thank
It's
you.
really nice. It really help us in teaching the things to student,
Hmm.
teaching the explain the things to student in a simple manner. Because at a point, okay, maybe from next sem I have to teach in a, I'm basically from a mechanical or production engineering, but I have to
Uh,
teach in a automobile engineering from a next sem. It's not sure,
uh,
but maybe I have to teach that subject. But I was unsure how I will proceed.
hmm.
But after attending this course, that now I'm confident that of course I will go in a very smooth manner.
I'm glad it's helpful. I think lots of people have put so much effort into making this course.
Yeah.
Right.
The
So,
way the sir write down the things, the way he note down the thing while speaking, and take out the pictures and the videos from the other slides, and note it down over there. So it's I'm also a faculty, so it's really motivating.
mhm,
We should go like this to teach the students.
mhm.
Yes, sir. Please convey my message to sir.
Yeah,
Thank you.
yeah, I'll certainly do that tomorrow morning when I meet him. Uh,
Yes.